In the previous video, we saw that infrared radiation causes vibrational excitation of the bonds in a molecule. There are many different kinds of vibrational excitation because bonds store vibrational energy in a number of ways. Bonds can stretch, just like a spring that's shown here, and they can also bend in a number of ways, two of which are shown here. This is a nice animation that I found on Wikipedia. Now in this class, we're mostly going to be focused on the stretching, and you see those in the top two squares, the symmetric stretching and the asymmetric stretching. Again, there are many types of bending vibrations, but bending will only be mentioned briefly in our course. We have seen that vibrating bonds will absorb infrared radiation to achieve a higher vibrational state, but it's also worthwhile to note that the reverse process also occurs in nature. That is, vibrating bonds can be demoted to a lower vibrational state by emitting infrared radiation. In this way, warm objects are able to release some of their energy in the form of infrared radiation. This idea has found an application in a wide variety of products. For example, some varieties of night vision goggles are able to produce an image in the total absence of visible light by detecting the infrared radiation emitted by warm objects. Warmer areas emit more infrared radiation, providing the contrast necessary to construct an image. More recently, thermal imaging has been promoted by alternative medicine practitioners as a method for the detection of breast cancer. This is based on the fact that cancer cells have inefficient metabolism and give off more heat than do normal non-cancerous cells, and that cancer cells promote increased blood flow to support the increased number of cancer cells in their inefficient metabolism. Data giving direct comparisons with mammography are very limited, but the data available suggests that thermal imaging is not as effective as mammograms for diagnosing breast cancer, and thermal imaging has a higher frequency of false positives, apparent cancer spots that are not in fact cancerous. The American Cancer Society and the FDA have taken the position that there is insufficient data to recommend thermal imaging in the detection of breast cancer. Now, when we think about organic molecules, for each and every bond in a molecule, the energy gap between vibrational states is very much dependent on the nature of the bond. For example, the energy gap for a carbon-hydrogen bond is much larger than the energy gap for a carbon-oxygen bond. And you can see that here we have a large difference in energy between the vibrational states for the carbon-hydrogen bond, and here for the carbon-oxygen bond, the difference in energy between the vibrational states is smaller. Both bonds absorb infrared radiation, but the carbon-hydrogen bond will absorb a higher energy photon. In fact, each type of bond will absorb a characteristic frequency, allowing us to determine which types of bonds are present in a compound. We simply irradiate the compound with all frequencies of infrared radiation and then detect which frequencies were absorbed. For example, a compound containing an oxygen-hydrogen bond will absorb a frequency of infrared radiation characteristic of the oxygen-hydrogen bond. In this way, infrared spectroscopy can be used to identify the presence of functional groups in a compound. And that's what the bottom line is with our infrared spectroscopy. We want to be able to determine or identify functional groups in an organic molecule. In an infrared spectrometer, a sample is irradiated with frequencies of infrared radiation, and the frequencies that pass through that are not absorbed by the sample are detected. A plot is then constructed showing which frequencies were absorbed by the sample. The most commonly used type of spectrometer, called a Fourier transform or an FTIR spectrometer, irradiates the sample with all frequencies simultaneously and then uses a mathematical operation called a Fourier transform to determine which frequencies passed through the sample. An infrared spectrometer measures the percent transmittance as a function of frequency. This plot is called an absorption spectrum, and we see an absorption spectrum right here. All the signals, called absorption bands, point down on an infrared spectrum. So we have an absorption band pointing down here, we have some here, we have some here. So all these things that point down, we call those absorptions or absorption bands. The location of each signal, or those absorption bands, on the spectrum can be specified either by the corresponding wavelength or by the corresponding frequency of radiation that was absorbed. Several decades ago, signals were reported by their wavelengths, measured in micrometers or microns. Currently, the location of each signal is more often reported in terms of a frequency-related unit called a wave number. The wave number is simply the frequency of light divided by a constant, the speed of light. And you can see the range of wave numbers on our plot is from 400 to 4,000 reciprocal centimeters. And notice that on our y-axis here we have percent transmittance. And so if the light was almost all transmitted, it would be up here. So that tells you that if you have an absorption band, right, the word absorption means what wasn't transmitted through. So since very little of the light was transmitted through here or here where the absorption bands are, that's why we call them absorption bands, right? Anything that wasn't transmitted through the sample gets absorbed by the sample. So again, that's why we can call these absorption bands or absorbances. Again, the units of wave number are inverse centimeters, or what I call sometimes reciprocal centimeters, and they range from that 400 to 4,000 range. All of the spectra in our course will be reported in units of wave number rather than wavelength to be consistent with what's commonly done by scientists today. Don't confuse the terms wave number and wavelength. Wave number is proportional to frequency, and therefore a larger wave number represents a higher energy. Signals that appear on the left side of the spectrum correspond to higher or high energy radiation, while the signals on the right side correspond to lower energy radiation. Every signal in the infrared spectrum has three characteristics: wave number, intensity, and shape. We're going to take a look at these three in the next few videos. Okay, let's talk a little bit about where wave number comes from. And if we think about the wavelength of infrared light that's used for infrared spectroscopy, so again, the wavelengths of infrared light that we're going to use for infrared spectroscopy, they will range from 2.5 micrometers to 25 micrometers. Now, if I convert those into centimeters, it's going to be 2.5 times 10 to the minus 4 centimeters to 25 times 10 to the minus 4 centimeters. Now remember, since energy is equal to hc over lambda, energy and wavelength are inversely proportional. So that means that my shorter wavelength should correspond to the higher energy and higher wave number. And my longer wavelength should correspond to lower energy and, of course, a lower wave number. Well, let's start by determining the frequencies of both of these wavelengths. So we'll start with the 2.5 times 10 to the minus 4 centimeters. In order to determine the frequency of that wavelength, I need to take the speed of light and divide it by that wavelength. But I'm going to have to convert my speed of light into centimeters per second instead of meters per second, since I have centimeters for both of my wavelengths. So I'm going to use 3 times 10 to the power of 10 centimeters per second divided by 2.5 times 10 to the minus 4 centimeters. Centimeters cancel out, and I'm left with 1.2 times 10 to the power of 14 times 10 to the power of 14 hertz. Now keep in mind that a hertz is the same thing as a reciprocal second. That's something you should be aware of. So if I do it for the other wavelength, I have that my frequency is going to be equal to c divided by lambda. So c is 3 times 10 to the power of 10 centimeters per second divided by my wavelength, 25 times 10 to the minus 4 centimeters. Those cancel out, and I'm left over with 1.2 times 10 to the power of 13 hertz, like that. Now, if I want to calculate the wave number for the higher frequency, my wave number is equal to frequency divided by the speed of light. And so it's going to be equal to 1.2 times 10 to the power of 14 seconds to the minus 1, right? Because hertz is the same thing as seconds to the minus 1, divided by 3 times 10 to the power of 10 centimeters per second. These cancel out, and I'm left over with 4,000 centimeters to the minus 1. Okay? And if we do it the same thing over here, we get that wave number is equal to frequency divided by the speed of light. So I have 1.2 times 10 to the power of 13 seconds to the minus 1 divided by my speed of light. 10 to the 10 centimeters per second. These cancel, and I'm left over with 400 reciprocal centimeters. And so this was merely done to show you where we get the wave numbers from. Okay, here are the wavelengths of infrared light that are used in the infrared spectrometer, and they result in the wave number range being from 4,000 reciprocal centimeters, which again corresponds to high energy, all the way down to 400 reciprocal centimeters, which corresponds to low energy.